Welcome. You're probably wondering where we are right now. Well, you're in what we call VR. And unlike other science videos that you might have seen before, in this video, you're not going to see one screen in front of you,
but everything you'll want to see will be all around you. This will mean that you'll have to look around to see the interesting things that are going on. The science that you're going to be seeing is going to be coming at you from all directions.
You might even say that you're going to be surrounded by science.
In fact, there's some science for you to see right now. If you look to your left, you will see me, or rather, the virtual reality representation of my voice as sound waves. And if you look to your right,
you'll see the representation of my voice. And now, since we didn't really have any large-scale computer equipment to work with, this is truly the extent of what we can animate for you. So if you want to continue our discussion about sound, we'll have to exit this realm and head to the real world.
In the real world, you can see people, but you can't see sound waves. If you could, you would see that they travel from my mouth to Ramy's ears by vibrating the air particles between them. That is, they travel from me
to me. Now, there are two major families of waves. We classify them based on how the disturbance is moving. The first, if I compress this slinky here, a part of it, and then let it go, you can see that the compression wave is now traveling from my hand to Mahmoud in the same direction as the slinky is being compressed in. Now this is what we call a longitudinal wave. Now among those are earthquakes and sound waves, which are basically just a compression of air between my mouth and your ears. Now the second type of wave is where the disturbance is moving perpendicular to the direction of the travel of the wave. For example, if you look at this, now as you can see, the slinky is going up and down, however the wave is still going from my hand to Mahmoud's. Now a very good example of these transverse waves are light waves. But we're not really interested in how waves travel. We're more interested in what happens when they meet.
We took a trip to university parks to find out. There's loads of water here, which is a great medium for making transverse waves, which are just made up of peaks and troughs. We can make these peaks and troughs by displacing the water, in this case by bobbing a balloon up and down. If we use two balloons, we can see what happens when the waves meet. They pass through each other, and they make these curious patterns. Let's take a closer look at these patterns in cyberspace. As you can see, when two peaks or two troughs meet, they add together to make an extra high peak or an extra low trough. We call this amplification, or constructive interference. And when a peak and a trough meet, we call the result destructive interference, or cancellation, because the waves cancel each other out. At certain points, it's like there's no wave at all. But can the same happen with sound waves? Can the noise coming from my mouth be turned into silence by shining another wave at it? Well, yes, and you can see that happening with one of these.
So, these are one of the instruments that are very important to any musician as long as they're coming from the 19th century. This is a tuning fork. And basically, these two prongs, when hit against an object, will generate a sound, and that sound corresponds to a certain musical note that musicians can use as reference to tune their instruments. Now, these two prongs act like the balloons we saw in the water earlier. They independently generate a wave around them, and these two waves, just like the waves created by the balloons, can meet at certain points, and at certain points they can cancel each other out. Now, I can make you hear that for yourself if you don't believe me, by rotating this tuning fork all around you. Now, when I do that, you are hearing all the space around the tuning fork. And at certain points, you can hear that the two waves meet, cancel each other out, and the noise that you hear goes down significantly. Now, why would you care about that? Well, you would care a lot, especially if you're designing a concert hall, an opera house,
or even a chapel.
When designing the interior of such places, we have to be very careful, because since the sound waves will be bouncing off the walls and interfering with each other, we want to avoid placing the seats in the spots where they destructively interfere, because there, the sound will cancel out and people won't hear anything. Instead, we want to place the seats in the spots where the waves are constructively interfering. That way the sound is higher and the people have a better listening experience. And this is really to show how universal physics can be. From the ripples of a pebble on the surface of a pond, to the interior of chapels and auditoriums. One single phenomenon can manifest in so many different ways. We hope that you have enjoyed this trip in VR with us as much as we've enjoyed making it. And thank you for listening.